Delighted to be here as part of the celebrations for David, and I'd like to thank the organizers for having me as part of it. By the way, is there a pointer? This one? Yeah. Okay. So the official title of my talk is String Theory as a Higher Spin Theory, but to follow a song from the 60s, I thought I would sort of subtitle this as a song for David. So when I think about my connections to David, it's very difficult to disentangle the different strands, in a sense, which have sort of tied me to David over the years, and for which I'm truly indebted. Of course, firstly, there is for being my guru, as they say in India, and it's been a privilege to have been a student and to have learned many things during the course of the PhD and afterwards. I still remember the intense sessions we used to have in his office in the cigar era, and also his beautiful classes on quantum field theory, from which I think I learned a lot. So there is that. But then I find that as time has gone on, I'm now at the ICTS and TIFR, and you heard Spencer say about how David was one of the people who steered it from its formative stages, and David continues to be the chair of our board, and in that capacity has been giving us invaluable advice. In a sense, with David you get real advice. I mean, you get starting from programs up to the tea service in the pantry, whatever makes the institute good. David has a definite opinion, and it's great. Coming more to physics, in a sense, it's quite it's sort of coincidental that, in a sense, the theme that I have been sort of interested in the last couple of years is something that originates with David. So David was one of the first people to emphasize and to try to make precise the idea of an unbroken symmetries of string theory, and especially in the tensionless limit. And this is an idea, I think, which perhaps the time is now ripe to address it. So that's sort of that will be the theme of this talk. Finally, he's also the inspiration for the title of this talk, and this, the official title, the String Theory as a Higher Spin Theory. And if this is not very clear, I just want to take you back something like 20 years when I entered graduate school. David wrote a paper on two-dimensional QCD as a string theory, and this was just about the time I was starting my PhD, and then in which he explored the parallels to string theory of two-dimensional Yang-Mills theory, and then he followed up. And he followed up a little later with paper on two-dimensional QCD is a string theory. So in that spirit, I mean, I hope that I will be able to give you a talk soon. I have a paper whose title is String Theory is a Higher Spin Theory, but at the moment it will be on string theory more as a higher spin theory. By the way, I mean, if you sort of put together this title with the title of this talk, two-dimensional QCD is or as a string theory, with string theory as or is a higher spin theory, you sort of get two-dimensional QCD as a higher spin theory, which I think, which is in a sense true, I think, and I hope maybe to present that to David at some point. So in any case, So David started with two-dimensional Yang-Mills. I will start with two-dimensional CFTs. Two-dimensional CFTs, of course, are nice because in many cases we know the spectrum explicitly. There's a sort of a chiral sector, which is the vacuum sector, and then there are the structure of the general partition function is something like this, so this is true generally, but there's a simplification when there's a large n limit. The simplification is that you can sort of factorize this thing into the vacuum part factorizes out, and then there's a sort of a simpler set of characters, what you could call the wedge characters sometimes. But more importantly is the fact that this thing, this factorized form, this can be viewed as a sort of a Fock space character. It's a sort of a multi-particle character, which is, so this is a sum over all the various primaries of the theory, the non-trivial primaries, but here you can sort of further organize this into a smaller, a sum over a Fock space character of a smaller set of primaries which are labeled by n, which in a sense you can view as the single trace primaries, and this y is a sort of a Young tableau index which sort of captures the multi-particling of a basic elementary single particle character. So this is a simplification in a sense that happens in a large n limit, or at least in 2D CFTs with a large n limit that have a holographic dual. So this is a general form of the structure of the answer, and this structure has a very simple interpretation from the point of view of the dual ADS3 theory. Sorry, what? Well, you can exponentiate that product. So I wrote it in a specific way in terms of this Young tableau, but that Young tableau is a different way of rewriting the usual exponentiation of the Young tableau essentially captures all the different ways of multi-particling the okay. You're right. Yeah, you're right. So in general, it would be a product over n and a sum over y. Yeah, in the particular case, we are considering actually n will be just one, so this won't appear. But you're right. So from a dual point of view, this from the ADS3 point of view, this vacuum character is essentially the multi-particling of the massless gauge fields of the massless gauge fields of the dual ADS3 theory, whereas this is the contribution from all the massive fields, which are labeled by n, these are all multi-particle characters. This should be a product, as Ofer pointed out. This kind of multi-particle expression from the bulk arises when you do sort of a one-loop computation. There's a sort of a trivial tree factor, but the structure is something that you would expect to see if you were to do a one-loop computation in the dual ADS3. And so let me show you how it actually works in a specific example. So in the case where the ADS3 dual is the simplest kind of Vasilyev theory, or bosonic Vasilyev theory, with a tower of massless gauge fields from spins 2, 3, all the way onwards, then that's the piece that would contribute to, these are the massless gauge fields that would contribute here. In this simplest Vasilyev theory, there's essentially one massive field, and in this case a scalar field. It's in a very special representation, which I will tell you more about later, called the minimal representation, of the higher spin symmetry algebra. So there's a sort of a global piece of the gauge symmetry of all these fields, and this is the underlying higher spin symmetry algebra, and there's a very specific massive scalar field, and in fact the masses and all the couplings of this matter field to the higher spin fields and to itself and so on is completely fixed by the symmetry algebra. So this is the symmetry algebra that's sometimes called the HS lambda symmetry algebra in the literature, so that completely fixes for you the mass of this field and all the interactions. So so if you do in the Vasilyev theory, if you look at the one loop partition function, what you find is you get contributions from the massless gauge fields, which, as I said, go from spin 2 to infinity, and there's a specific contribution, which is the Vasilyev theory? No. The Vasilyev theory has equations of motion. When you have the scalar field, there's no Lagrangian. Without the scalar field, there's a Chern-Simons-like formulation, but there's no known Lagrangian in the presence of this, the massive field. But for the one loop determinant, you just need to know the quadratic part, which is known, which is essentially fixed by the gauge invariance and the masses, as I said, of the scalar field are also known. So you can compute these determinants explicitly, and you get some explicit form like this. So this is that of the scalar, and that's so this is the thing that matches with large n CFT, in this case large n limit of minimal model CFTs. So this this match is has this piece over here coming out to be the vacuum character of the CFT. In this particular case, in the large n limit, it's a vacuum character of W infinity, and these characters are just the Fox-based characters built from a basic single particle character of, as I said, the minimal representation, the dual of the minimal representation, which the scalar field is. So in the CFT, this is a simple representation. It's simple in the sense that it has the smallest number of states at any given level. You see its character is very simple. There's just it's just the descendants are just 1 minus given by this 1 over 1 minus q. So essentially at each level, instead of the potentially all the different descendants that you could have from all these W infinity currents, they are all mostly proportional to each other, and that's why you have essentially one non-trivial state as a descendant. So this is a representation which has lots and lots of null states. So it's a sort of a very small and very special representation. And just keep this in mind, because there'll be a very similar parallel to this in the string theory. So this is the statement here. So you have just one, the whole CFT with all its many non-trivial primaries just can be viewed as a multi-particle of a single basic representation, or in the dual theory, a scalar field. So, okay, so with that, so one lesson you could sort of draw from there is that if we knew only the CFT, the minimal model CFT, in a sense you could have deduced the Vasilyev, the presence of the Vasilyev gauge symmetries and the representation of the matter field from just knowing the partition function, and you could, in a sense, try to reconstruct the bulk from there. So we try to use this philosophy, or use this as a model to study 2D CFTs, which are in a sense dual to string theories, and more specifically string theories at sort of a maximally symmetric point, at the analog of a tensionless point, where you hope to uncover the most unbroken symmetries. And so the candidate CFT is of one of the most canonical backgrounds that one has for ADS3, the ADS3 times S3 times T4 background, and there's the symmetric orbifold CFT for the dual D1, D5 system, which is essentially a symmetric product of 4 free bosons and 4 free fermions. So we'll try to understand the unbroken symmetries of this CFT, and from both from this general viewpoint that I sort of sketched out, and in particular keeping in mind the Vasilyev symmetry, which we'll see is a subset of the unbroken symmetries, and then moreover try to understand how these symmetries organize the matter fields. So we saw the matter fields are, I mean, the gate symmetry is just a small part of the spectrum over here, and we would like to see how the matter fields are sort of organized under this as well. So it's sort of, okay, there are many levels I could answer that question. So the first is that it's free theory. It's the analog of the free Yang-Mills point, which is where you have, in the higher dimensional cases, that's where you have an unbroken, the maximally unbroken symmetry, which is also sort of, if you naively extrapolate the tensionless limit, the Yang-Mills coupling going to 0 in n equal 4 Yang-Mills is what you would think of as the tensionless limit of the string theory on ADS5 times S5. This free point here is analogous. As we'll see, it shares many features with the higher dimensional cases, in particular having a similar Vasilyev symmetry at this particular point. And so I think it's the one that, as far as we know, qualifies as the closest analog of the tensionless limit. Yes. So S3 times T4 with Ramond-Ramond fluxes. So on the moduli space of the well, it's you can so in higher dimensions there is in higher dimensions you can take the dimensionless Yang-Mills coupling as the radius, as a measure of the radius in string units, and it's going to 0 is what you would think of as the tensionless limit. So if you wish, if you don't like the terminology, but I think this is the closest analog of the terminology. Yeah, so it's whatever is the point that is, I'm not insisting that there is a invariant statement is that there is a point with maximally unbroken symmetry, and that's the thing that I think qualifies most to be called the tensionless point. So yeah. So the symmetric product CFT is a free CFT. It's a free orbifold CFT. It has a general structure which is which has the vacuum sector. Then there's a sort of an untwisted sector, sort of refining a little bit the more the one that I showed you right at the beginning. Among non-trivial primaries, there are ones in the untwisted sector and there are ones in the twisted sector, and there's a large vacuum sector. So we'll take the large n limit, of course, of this CFT, and in the large n limit, it's easy enough to write down expressions for all of these, but we'll focus first on the untwisted sector, so namely the first two terms over here, and that has a simple product form, as as given over there. So this is, if you wish, a generalization of the sort of product forms that I showed you earlier in the Vasilyev theory. It's just, it just looks a little bit more complicated. The exponent here is given by the by a generating function, which is the generating function of 4 free bosons and 4 free fermions. And so it's a known set of numbers. Once again, like we saw for the case of the minimal model CFTs, this answer can be written as a Fock space character. So you can take out this vacuum sector, and what you get is essentially a multi-particle character of a single basic entity, which I will describe to you. So again, we don't have a sum over or a product over n. We have basically one the single particle character whose multi-particling gives you all of this. So this is something you can see explicitly from this form. Yeah.
Shouldn't the product for the fermions have been 1 plus in the numerator?
So there should have been a -1 to the 2r. I don't know if, maybe I missed. There's a -1 to the 2r and 2r. Yeah. And so yeah, this is not the index. This is the full partition function, so everything comes with plus signs. So that's why this D also comes with alternating signs. It has minus signs in the numerator, so this D comes with minus signs, so that these are in the numerator or denominator, depending on bosons or fermions. So this is, as I said, this whole thing is built from a single wedge character, and you can, in a sense, view this whole piece, this piece of the partition function, as a gigantic higher spin theory. So, as I said, it's very parallel to the higher spin case that we saw earlier, except on a much larger scale. So the vacuum sector that I had in the previous transparency, which I denoted by Z tilde, is actually something like this. It's just a sort of the chiral part of that generating function. So this is the sort of the stringy answer that we had. This is in contrast to the Vasilyev answer that I showed you for the minimal models, where it's where the exponent here is just grows with r. That's a reflection of just the fact that there's one gauge field at every spin, whereas over here this d grows exponentially because it was given by the generating function of the 4 free bosons and the fermions, so that has a sort of a Cardi growth. So the numbers that appear here are much, much bigger than the numbers that appear here. So it's exponentially larger, and it's this structure. So this chiral sector is much, much bigger than the Vasilyev chiral sector, and this is what, for reasons that will become clearer later, is what we call the higher spin square, or HSS, in contrast to the HS. So anyway, that's what the CFT tells you, that there's this big chiral sector, and this wedge character that we had. Yeah, you had a question. These are massless highest. These will correspond to the massless highest spin fields. Yeah, exactly. So this is very special. I don't know if I'll get a chance to say this, but let me say it now. ADS3 is very special because the unitarity bound for conserved currents is just delta equal to j, not delta equal to j plus 2 as in 4 dimensions, or delta equal to j plus 1 in 3 dimensions. So the things that saturate this are much, much bigger than in higher dimensions, where basically it's only the bilinears which saturate this bound.
Is this as big as the Algebraic?
No, it's not e to the r. It is e to the square root r. So it's still not really full-blown unbroken stringy symmetry, but it's somewhere on the way. Yeah. So it's so that's why there's there's a large massive lots of massive trajectories. But in the untwisted sector, all of them just basically come from one field in the bulk, and its character is something like this. In contrast to the one that I showed you earlier, which was small. So this is certainly much bigger. There's a sort of product over n. This is itself growing very large. The number of states at any given level is quite large. But this is a single character of this big chiral algebra, just like this was a single character. And in fact, I'll try to tell you it's very similar minimal character of this unbroken stringy algebra. So, so to do that, let me remind you of an element of the Vasilyev construction. So the Vasilyev higher spin symmetry algebra is basically built from two oscillators, which Vasilyev calls y hat, and these oscillators obey a sort of basically an oscillator algebra, slightly deformed. So this is the two oscillators, alpha goes from 1 to 2. So this is just a usual oscillator algebra. There's a small additional piece which depends. This lambda is the parameter of the HS lambda, which defines the inequivalent higher spin algebra. So it's just a number. You can think of it as something going from 0 to 1. In our case, actually, it will be either 0 or 1. This k is kappa is a special operator. It's not very significant for our purposes because it basically distinguishes, it takes eigenvalues plus or minus 1 and distinguishes sort of left and right moving sectors. But basically I want to tell you that this, the higher spin symmetry algebra, the way Vasilyev constructs it, is basically from two oscillators. And arbitrary monomials in these oscillators give the generators of the higher spin fields, or equivalently the higher spin currents. So in particular, for instance, if you take the quadratic generators in the Y's, those give you the SL2R subalgebra, which is the gravitational subalgebra. So the L0, L plus minus 1 are built from bilinears in this. The spin 3 currents are built as sort of quartic terms in this and so on. So it's sort of 2 times S minus 1. So this is the basis of his construction, and then he constructs sort of big, sort of a super field built from these oscillator algebra, and then he writes down the equations of motion and so on. But this sort of the algebraic ingredient of the higher spin symmetry algebra. So what's happening in this higher spin square case? The vacuum algebra over here, as I said, is much bigger. But as we saw, it's in the vacuum algebra is essentially in correspondence with the chiral sector of a T4. That's what these coefficients D, this D of RL, the generating function, essentially captured the fact that the single particle states are in one-to-one correspondence with the chiral sector of T4. It's important to note that this is sort of a correspondence in the sense that we take a single copy of T4, build a current, and then just take the sum of all the n copies, and that's the object, that's the part of the chiral sector of this theory. This is the single particle state in the large n orbifold. But of course, there's a one-to-one correspondence for every such operator, single cycle or single trace operator that you can build. There's a piece of the chiral sector of T4. And these are all independent generators at large n, unlike the usual chiral sector of T4, where del phi square and del phi to the fourth would not be independent generators. But here, these are all independent generators because we are taking it at large n. So all of these are independent single particle currents which generate the whole chiral algebra. But knowing this, it tells you that you can generate this algebra by basically monomials built from the usual free bosons or free fermion oscillators for this T4. So you just need to, so I'll just stick to bosons, or one boson for simplicity instead of 4 bosons and 4 fermions, but basically it's the usual oscillator algebra. So there's this big chiral algebra, which unlike in the Vasilyev case where the whole algebra was generated by 2 oscillators obeying the oscillator algebra, here you have an infinite number of oscillators, that of that corresponding to 4 bosons, 4 fermions. But the Vasilyev subalgebra, there's a Vasilyev subalgebra sitting inside this in a way analogous to the way SL2R sits inside the Vasilyev algebra. So we saw earlier that the quadratic terms in the y's corresponded to the SL2R, the L0 plus minus 1. Here, the quadratic terms from these alphas will correspond to the Vasilyev subalgebra. And that's basically the usual bosonic, the W infinity construction that people had long ago from free bosons or free fermions, just from their bilinear currents. You generate W infinity algebra. So this is sort of analogous to that. It's a different set of oscillators, an infinite set of oscillators, but it's the Vasilyev subalgebra sits in a way very similar to how the SL2R sits inside the Vasilyev. This parallel continues to the minimal representations. So I had mentioned in the higher spin case, the minimal representation is sort of the smallest representation. That's because you can think of it in the language of these oscillators as one which is generated by a usual kind of a Fock space, a usual kind of an oscillator Hilbert space, which with a ground state which is annihilated by one of the oscillators. So we had y1 and y2, actually y1 hat and y2 hat, and one of them annihilates it, and the other one, of course, you generate all the states, and that's precisely what gives the character of q to the h over 1 minus q, because you have one state at every level. And this is a representation of the higher spin algebra, clearly, because, as I said, the higher spin generators are built from these y's, and so they act on this, and sort of there's a simple representation. This is the sort of smallest representation, and the matter field of the Vasilyev theory is precisely this representation. So similarly, you can define a minimal representation of this bigger chiral algebra, the higher spin square, in a very similar way. From the oscillator algebra, again, you just look at the usual sort of conventional ground state, which is annihilated by the positive modes, and then you generate all the whole Fock space from the negative frequency modes, and you can again argue that this has the smallest number of states amongst all the representations of this much bigger chiral algebra. It has sort of many null states again, so for instance at level 1 you have just basically 1 or 2 a handful of states, as opposed to the infinite number that you would generate in principle from all the higher spin current modes. So the structure of this representation, the minimal representation, which was the building block of the matter sector of the symmetric product, is very much analogous to that of the higher spins case. And in fact, so this is not just an analogy. You can, because the higher spin theory sits as a subalgebra of this much bigger higher spin square, you can decompose all the representations in the representations that we considered, both of the currents as well as of the matter fields, in terms of infinite number of the higher spin representations. So this was the basic matter field in the symmetric product. and you can write it as a sum over different representations of the W infinity Vasilyev algebra, of which the first non-trivial one is the minimal representation of the higher spin algebra, but there are an infinite number of others as well. So these are the the right hand side are W infinity representations, which start with the minimal representation of the Vasilyev theory, and this whole infinite tower builds up the minimal representation of this much bigger chiral algebra, so in fact, most of the representations that appear over here in the Vasilyev vector type holography, they would have appeared as multi-particle states. These were the sort of things that appeared in the Fock space character, but here they are sort of single particle representations in the string theory, and this is a bit like the way in which you go from, when you go from vector models to matrix models, what were sort of multi-particle states become single particle states in the sense of you can have sort of phi to the n, trace phi to the n. So in fact, all the couplings of these, so if you view this bigger bulk theory as a gigantic higher spin theory, the couplings of all these to the Vasilyev fields are in fact determined in terms of those of the minimal higher spin representation, because the multi-particle couplings are sort of determined by the single particle ones. So this whole higher spin square plus the minimal representation is you can view as a sort of a souped up Vasilyev theory, except that its symmetry algebra is not the usual symmetry algebra of the Vasilyev theory, which was a higher spin algebra, but it's instead this much bigger higher spin square algebra. But in principle, you should be able to take the whole Vasilyev construction and construct the Vasilyev equations of motion based on this much bigger higher spin square. So this higher spin square, let me just explain the terminology, the name, because so this is a much bigger algebra, as I have stressed. So you can decompose it in terms of the higher spin representations. And the decomposition is fairly simple because, as I said, the higher spin algebra is essentially oscillator algebra, and the higher spin square algebra is an oscillator algebra, and so you can organize things in terms of monomials of these oscillators. The quadratic ones were the W infinity or the bosonic Vasilyev generators that I mentioned earlier, but there are cubic ones, quartic ones, and so on, and all of them transform in specific representations of this Vasilyev subalgebra. So this bigger chiral algebra can be decomposed in the single particle currents can be decomposed in a very simple way in terms of by just grouping them in terms of monomials, and they are indeed specific representations. But interestingly enough, there is another way to organize the currents. This is by slicing through that diagram horizontally instead of vertically. I arrange things in terms of columns. You can arrange them in terms by taking the top row of each column and fermionizing it, in which case the top row was something like del phi to the m. So m goes from 1 to infinity, but these can be written in terms of bilinears of fermions, and then the others can be written in terms of the dual. In terms of fermions, these would become sort of quadratic terms in the fermion. These would be sextic terms and so on. This would be quartic terms, sextic terms, and so on. So there's a different way to sort of slice it in terms of a different algebra, which is the bilinears of fermions. That's what we call the horizontal algebra. It's a different W algebra associated with fermions. The earlier one, the earlier vertical slicing was associated to bosons. So in a sense, there are two decompositions. The The vertical decomposition is in terms of the bosonic W infinity, and there are a certain set of representations, and that there's a certain that corresponds to a certain character decomposition, in this case of just a single bosonic oscillator, in terms of all these representations, whereas the horizontal one is in terms of a different W infinity with a different parameter and a different set of representations. The various fermion composites are that corresponds to a different slicing, and there's a different character identity corresponding to this slicing. So the nice thing is that you can put both of them together, and that generates the whole. In a way, you can. That's a simple way to characterize the full algebra of this higher spin square in terms of the commutators between different elements are completely specified in terms of these two W infinity, the horizontal and the vertical generators, because different rows and columns transform in known representations of each of these. So that makes that completely determines the all the commutators. So I'm more or less done. So what, in a sense, I've tried to show is that there's the string theory on AdS 3 times S3 times T4 has a very large unbroken symmetry algebra that is sort of very much parallel to the higher spin symmetry, but except that the algebra is exponentially larger. But nevertheless, it is completely determined by the higher spin symmetry because of this square structure. The matter sector also parallels, at least in the untwisted sector, it parallels the higher spin theory in that it is built from a very special representation, this minimal representation, and hence it's sort of the minimally coupled field, if you wish. The twisted sector is something that we are currently exploring. It seems to have a nice structure as well, in the sense that the corresponding representations, there are matter fields now in the twisted sector. They are labeled by the different sectors, can be broken up into single particle ones labeled by the cycle. These seem to be sort of near minimal representations. They seem to be the next bigger representations compared to the minimal ones. But there are some complications which I can tell anyone who is interested later. But I think there's a nice underlying structure which one should be able to understand in the group theory of this higher spin square. So finally, I mean the whole idea of this, the whole philosophy here is sort of to follow Vasilyev theory, which is a model in a sense for how constraining the extended gauge symmetries can be to describe a bulk theory. The fact that there are all these many different gauge invariances sort of having to mesh together essentially fixes the dynamics. You would hope that by uncovering this symmetry algebra, you should, just as Vasilyev's equations essentially were fixed by the gauge invariances, this big unbroken gauge invariance should help to should result or should be the reason for a similar rigidity for the string theory, including the interactions, just like the interactions in the Vasilyev theory are completely fixed. You would imagine for the higher spin square, in a sense, a parallel Vasilyev-like construction. It gives you the full nonlinear theory, including all the interactions. This is something that we hope to do to show that you can construct the full bulk theory as a big Vasilyev theory, except for a much bigger algebra. And perhaps this will go some way towards explaining something that David is always kept asking, I think, of generations of string theorists, why string theory is unique. What is it in string theory that makes it sort of, what's the underlying principle that sort of fixes it rigidly. So, so hopefully we will get there soon in time, maybe for your 80th. So thank you.
I have a general philosophical question for production. In the old days, people thought that if you go to short distances, is the true symmetry of the field. The modern perspective is exactly the opposite. Whatever you get, whatever symmetry you get at long distance is emergent. And at short distance, you shouldn't see that. Well, completely. Well, we know that's wrong.
For in,
In the old days, you thought you go to short distance, then you see SU5 is better. If you just explore a theory of shorter distances, the true underlying symmetry will be exposed.
no, I agree.
First of all, these symmetries better not be global symmetries, because they are getting global symmetries. But even if you expose some gauge symmetries at short distance, this is an artifact of all sorts of things. These are emergent symmetries.
I'm not so sure in the case of gravity. I mean,
That's because it happens, if indeed when you get to 5, it happens that then it will be below the Planck. Yeah. But when you go to strength,
But SU5 still has implications.
oh yeah, no, I have no problem with SU5. I said that was in the spirit that you go to shorter and shorter distances, you see bigger and deeper symmetry. But the modern problem is that only gauge symmetries are emerging symmetries. SU5 might be good, it might have implications. In the context of string theory, if you go to very high energy, you will not expose, you will expose something interesting about the structure of the fluid. But whatever it will be, it will not be the underlying symmetry.
so maybe the symmetries, yeah. No, so I think, so I mean, how do,
So symmetry is the answer to the question regardless of what it is.
no, so just like the
For the time being, when you find the answer, you get a better explanation.
I mean, after all, I agree that the philosophy of emergent symmetries, but I think in the case of gravity and in the case of string theory, which seems to be the only ultraviolet completion, there seems to be a structure that sort of rigidly demands that there's a certain rigidity in it. You can't tinker around with it, and that is not manifest in at least any perturbative formalism.
This is just the zero.
Let's say it's zero coupling, yeah. The large n limit, so it's a classical.
So far. Yeah. I have no problem with rigidity, but I don't see where rigidity is anything to do with symmetry.
Yeah. I mean, just like.
Symmetry is an example of something that organizes structure and gives rigidity. It's clear that there isn't any symmetry in the usual sense, the underlying symmetry. Not even lots of examples of symmetries that are related to rigidity.
That's correct. It just sounds a lot better to talk about symmetry than rigidity. Or organizing principles. Sounds too rigid. But it seems obvious also that the secret of the rigidity, or whatever it is that underlies uniqueness, is at short distance. As you approach whatever short distance means, that short distance will be exposed. No, I have no problem with that. My problem is only with the word symmetry.
Yeah, I mean, it's like, okay, the Vasilyev, let's take Vasilyev theory as some prototype of some kind, assuming it were quantum mechanically complete and so on. But it's a case where the interactions are sort of the principle of gauge invariance, which I agree that gauge invariance is a sort of a notion of redundancy, but it helps you in sort of
I would say it's exactly the opposite. Vasilyev's high-speed symmetry is an emergent symmetry in the infrared. So what you exposed here was not a more fundamental theory of short distance, but instead another symmetry that string theory can exhibit in the infrared.
but it's not in the infrared. It's
Only exists in
ADS, but and also in a very short, I mean, the tensionless sort of limit of ADS, so which is where you're probing essentially stringy scale. Okay, anyway.
Called background defendant. technical thing. Can you, so you have Vasilyev and you construct a square, and you get sort of the square root of the Hagedorn spectrum. So if you were to, what do you have any thoughts about going out
towards a
to
Hagedorn?
third dimension, or, I mean, do you need a cube or infinite?
So at least in ADS backgrounds, I don't see any point in the moduli space where you, in the maybe the kinematic regime that you originally considered, where all amplitudes were essentially related to each other, that if one could sort of connect some of this with that, perhaps it will give you a clue of how to go beyond this. But
But just mathematically, how far do you have to go building on HSS?
I think the Vasilyev construction is fairly general. I mean,
I think they're just going to take HS cubed and
oh, HS cubed. Yeah. Well, yeah. That I haven't thought about. I don't know whether there's, whether there's any obvious structure that would go in. So even this is, when I say it's, the square is not a tensor product in any sense. It's sort of putting together all these representations and then building this exponentially larger algebra.
Obvious way of actually going to the
In a third direction, I don't know of one.
In the untwisted sector are different states with different momenta, all in different representations.
Momenta on the torus. So right now, I'm not taking things which are charged under in the torus.
So you're like R4 rather than.
Yeah.
But if you were on the torus, but even on R4, you'd have different momentum sectors. Just the guy moving.
Yeah, so you mean e to the k dot x? No, those I think would be different. Different.
And other representations, basically those labeled by the momenta and winding. The matter
I would think so, yeah, because it's the oscillator this thing. So they would be isomorphic because they'll have a center of mass k. That's all.
So for each momentum, you have one matter.
Yeah, but they are all similar representations. Yeah.
And suppose we looked at the twisted sector of length 2, cycle of length 2.
That's that's a different kind of representation.
Different kind of representation, but once again you would have
for each cycle, yeah, 2, 3, 4, there would be.
For each cycle, for each momentum and winding, you would have a matter.
Yeah, but they would be all isomorphic. But the inequivalent ones would be for every winding.
Right, but we're just counting the matter.
There would be for each of them.
Winding and length of cycle.
Yeah.
3 integers later.
Yeah, so that's why, because this is the whole spectrum is Hagedorn. This is sub-Hagedorn. So you can't do it with just a finite number of representations. You can't pack the whole thing into a finite number of representations.
So it's a very small number of representations, just 3 integers.
Labeled by a few denumerable sort of setup.